And for the induced tissue regeneration, now that's the telomerase part of your company, correct?
Well, you said you were kind of amazed by the science. Now I'm going to lose all you and your listeners because you're going to say, no, I was kind of going along with this guy, this is kind of neat stuff. And I Googled telomeres and telomerase and wow, some people are, our old collaborators got Nobel Prizes for it. Liz Blackburn and Carol Greider, stuff like that. Yeah, wow, that looks real. Yeah, Nobel committee thought so. Yeah. Then I'm going to tell you about ITR, and you say, okay, so this guy went off the rails. Let me tell you the ITR story. Let me tell you the story. It's not a story. It's real.
I'm excited.
But it's new. And you're not going to find a lot about it online. There was actually just an article written in the New York Times a few days ago. I think Nicholas Wade wrote it. And he cited Lenny Guarente at MIT saying, this is a big deal. So, I mean, it's starting to get out there. So what's the deal? I began with Dolly the sheep. Back to the birds and the bees here. So normally life begins with a fertilized egg, as we said. Well, turns out something that no one thought would ever work. If you take a cell from the body, a somatic cell that ages and is immortal, right? It's differentiated too. It's now a skin cell or a heart cell or whatever. If you take that cell and its DNA, its little blueprint of life, and you put it into an egg cell, the egg cell will act like a time machine. And it reverses the aging of that somatic cell and takes it back to an embryonic state. And if you put that cell into a uterus, you can generate an animal identical to where that cell came from. So that's cloning, of course, somatic cell nuclear transfer, SCNT. So Dolly was cloned from a cell from breast tissue. They named her after Dolly Parton. It's a typical humor of a overworked scientist. So what was once a breast epithelial cell was put into an egg cell, and the cell was taken back in time, and a young lamb was born. And I was really entranced I thought that this was reversing aging itself in a cell. I bought the U.S. cloning effort. It was a company called Advanced Cell Technology and the animal cloning company. My old company, Geron, which I had left, bought the Dolly Roslin company. And they published in Nature, this prestigious magazine, that it didn't reverse aging. So Dolly was indeed a lamb, but she was a lamb and she was a sheep in lamb's clothing. She was actually born old. And a lot of people believe that. That's kind of a myth out there. We published a year later, in the year 2000, in Science, another kind of competing journal, that in cows at least, somatic cell nuclear transfer, when you take an aged cell from the body and you put it into an egg cell, the egg cell acts like a time machine, and we showed that it reset telomeres. It activated telomerase and rewound the clock, and the resulting baby cow was born young, totally normally young. Now, why do I tell you that story? I thought that was truly magic on multiple dimensions. One, that the process of making a body, that arrow we call development, could be turned into reverse. I mean, why would it go? It never goes in reverse in nature. How could that possibly be true? And secondly, that something in the egg cell reverses aging in the truest of sense. I had to study this. And so beginning around 88, 89, that's all I worked on for years and years and years. And we published in 2001 the first, right around the time that Bush had approved, talked about the embryonic stem cells, we published the human nuclear transfer, taking a human cell in a ride in a human egg cell, a human time machine. That was a little controversial. President Bush vehemently disagreed with us, ordered the patent office to remove one of our patents after it issued. And we were kind of at war with President Bush on that issue. Our intent, I think, was misunderstood. Why not was? We weren't trying to clone people. We were trying to clone cells. And I wanted to find a way to reverse the aging of cells. Well, over the years, we found the molecules in the egg cell that are like telomerase, that is capable of immortalizing a cell. We found the genes, in this case it was several genes, that are capable of acting like a time machine. So just like if you put telomerase into Len Hayflick's cell, it can extend the telomeres of a cell and immortalize the cells. By putting these ITR genes, we call it induced tissue regeneration, ITR, it can take cells back in time. And what we're doing is developing it to take cells back in time in the human body. So we're working on delivering telomerase and these reprogramming genes, as we call them, into the human body to take your cells literally back in time, to reverse the aging of cells and tissues in the body in the truest and fullest sense of the word. Is that possible? Well, we haven't published much of our data. We published some at AgeX, we published some basic science, but we have two competitors in the field, friendly competitors, I would say. One is Turn, T-U-R-N, like turning back the clock. They're a group out of Stanford. They just published this paper, which was written up in the New York Times. And they're seeing that these genes reverse the aging of tissues of various kinds. The other competing effort is David Sinclair's group at Harvard Medical School. And they published that when you put these genes into the eye, you can reverse the aging of the eye and induce a characteristic that cells and tissues have when you're very young, when the body's first forming, to naturally repair itself in a very profound way. And so that's why I call it induced tissue regeneration, or ITR. This technology is the most profound science I've ever encountered in my life. And I believe it's going to be really history in the making. It's what's no one's expecting to happen. I think no one thought we'd ever reverse the aging of cells with telomeres or cloning, that you could actually clone an animal, but actually reverse the aging process. I mean, literally, in the body of an animal or a human. Aging researchers never thought that was possible. Slow aging, sure. We knew we could do that. Extend human lifespan or animal lifespan, we've known we could do that for years, 30% or something. But reverse the aging of an animal or a tissue, that's an eye-opener. I'm sure the average listener will think, oh, that just simply can't be true, but it is true. And that's what the public will be hearing about, I'm sure, over the next few years as papers are published.
And so let me ask you to put the significance of this into practical terms so people can really wrap their mind around it. When you say reversing our cells, reversing the aging of our cells, I mean, what exactly does that mean? Are we saying that with this therapy, I'll be able to go back to being a child? Or what exactly do you mean by this?
Benjamin Button, yeah, right. No, so, well, I guess we don't know because we haven't done it in a human, but I wouldn't think so. The growth pathways appear to us in all our, the modern medical technologies are incredibly powerful, with this RNA sequencing and everything. It's just so much data. And it appears that the mechanisms that control the size of the human body are separate mechanisms from those that are controlling aging. At one point, some scientists thought maybe they were the same, and they thought that aging was sort of a mechanism to prevent us from becoming giants. We stopped growing when we reached adulthood, and that same process was causing us to age. I don't think that's true, and I think most biologists don't believe that that's true. So if we reverse the aging of a tissue, we don't think you would literally get smaller and smaller and become a baby. What we think is what would happen is that the way we're designing this technology is that you would induce molecular mechanisms that really you don't even have when you're born, an intrinsic ability to repair your body scarlessly. Like in a heart attack, early in development, you have a heart attack, the body just regrows new heart muscle. And we believe we can reawaken that and reverse and add back telomere length through the use of telomerase, but allow the body to kill off old cells naturally and replace them with young, healthy cells and rebuild the body in a healthy state, but without regressing size and development. We think that's a pathway commonly called the hippo pathway, like the hippopotamus that controls body size. We think it's different. So, but how all this would work is this is entirely new technology, and right off the lab bench, I'm just kind of giving you a glimpse where the science is at the moment, and the current animal data looks extraordinary, and the science is very strong, and we're quite excited about it.
I'm excited about it as well, Mike. This is really, really cool stuff. So let me make sure that I'm following along with everything that you've said so far correctly. Basically, I mean, it's not going to be Benjamin Button, not likely, but
Right.
But what it is going to be is, if we have chronic injuries, if we have a heart attack, I mean, anything like that happens with this induced tissue regeneration, it will be able to heal you 100%.
That's what we're aiming at. I think it's possible. We had that. Let me put it this way. We know it's well established that we can reverse the aging of your cells all the way back to the beginning of life, right? You know that, right? That's called induced, not tissue regeneration, but induced pluripotency, iPS cells. So I can take your cells back to day 6 of development and then make beating heart muscle in the dish. And it's your heart muscle that you had in the first few weeks when your body was forming. We know that. That's well-established science.
Sorry, but that is also insane.
Yeah.
It's just so cool. But go ahead.
I know it's insane. It's cloning, but I used to call it analytical, cloning. It's cloning without using the egg cell. It's using molecules that do all the work. And it's called induced pluripotency. So we know that we can reverse time zero and truly make all these age markers go in reverse and take you all the way back to the cells you were born from. Now, if I did that in you would just be this green, pile of cells. You'd lose all of your differentiated cells. You'd be slime, and that's not a good thing. So instead, what I'm describing here is taking the train ride instead of back in time all the way back to the beginning of life, jumping off the train partway. The majority of scientists call it partial reprogramming, and that's the concept. You're taking this miracle of reprogramming, of taking a cell back to the beginning of life, but you're only taking it part way and you're jumping off the train. And like I said, we all had, when our bodies were first forming, we had this amazing ability to repair a tissue. If you go into a baby that's just forming in its mother's womb, and you cut the skin, in 72 hours, the skin's completely normal in appearance, scarlessly. And if you took a chunk out of their heart or induced a heart attack, and you, of course, do this in a mouse or something, not a human, it can regenerate. The spinal cord can regenerate in humans. We know that from some data. So what we're interested in doing is taking the cells in your body back to that early stage and then letting them go back and forward in time again, and also resetting telomere length. Why am I optimistic about the outcome? Because nature shows us that such a reactivation of regeneration and telomeres can thwart aging. So some animals can regenerate profoundly and have telomerase all the time, and they don't get cancer, and they don't age. So, you know, these little planaria, you've seen these little flatworms, right? They have two buggy eyes and crawl around. You can cut their head off, and their tail will grow a new head, and their head will grow a new tail, and you can do that forever. They're said to be immortal under the edge of the knife. And they can regenerate, they have telomerase, and they just keep going, and there's no aging in those animals. And there's more complex animals. There's an animal in, I think it's in Slovenia, called the Olm, O-L-M, and it can regenerate and presumably has telomerase. So I haven't seen definitive data yet on that. We know it can live at least 100 years, and most people think it's an immortal vertebrate animal. So the ability to regenerate and for our cells to replicate without a Hayflick limit, we think are the two most profound means to intervene in aging been found to date. That isn't to say, you know, there's other strategies, there may be, but animals that have the ability to regenerate and can do it endlessly typically don't age. So regardless, these will be very important in medicine. You know, I mean, the ability to regrow a heart after a heart attack and the ability to induce that would be all by itself, you know, a very important advance, of course.